Okay, welcome to boot camp video number 4, in which we finally start talking about chemistry. So the topics we're going to talk about in this video are the elements of the periodic table, and then the chemistry concept of the mole. So let's get started. So everybody, I think, at some point in their life or another has seen a periodic table. Those of you who have had chemistry at St. David's already obviously will be quite familiar with this. The rest of you, I'm sure you have seen it in your physical science in middle school or just in the public domain. And so this is a listing in ascending order of atomic number of this is actually now out of date because there are now 118 named elements, and they are listed in order of ascending atomic number, and atomic number actually corresponds to the number of protons that are in the nucleus of a given atom. So do you need to have the entire periodic table memorized? No, you don't. You will always have a periodic table available to you on tests and quizzes as a reference. However, I do have a subset of elements that I want you to be able to correlate name with symbol for, and there are 45 of them. And I'm going to put this handout in the worksheets folder for the boot camp. I will also give this to you at the beginning of the year in class. But this has symbols and names of 45 common elements, and they represent, and how did I come by this list of 45? Well, there are, first of all, the first 30 elements of the periodic table are all listed here. And then in addition to that, there are another 15 that are important for various reasons. Several metals that are known, been known since from antiquity, like mercury and silver and gold and lead, etc. And then some other important elements like bromine and iodine and radon and xenon, and we'll get into why those are significant a little bit later in the course. But you will need to be able to correlate names with symbols for these 45 elements. Now, going back to what an element symbol looks like on the periodic table, every square on the periodic table represents a different element. In the middle is going to be what's called the element symbol for that element. Here I've chosen chlorine. Above that is going to be a number, that's its atomic number. So chlorine is element 17. And so the 17 at the top is the atomic number. And then there's always a number at the bottom. That is the mass of one, that's the atomic mass, that's the mass of one chlorine atom in AMU. And AMU stands for atomic mass units. Atomic mass units are extremely tiny. One atomic mass unit is equal to 1.66 times 10 to the minus 24th grams. So it is a very nearly infinitesimally small number. But a chlorine atom weighs about 35.5 of those AMU. Now, this is useful information, particularly the atomic mass, because it allows us to do some calculations. And so just sticking with chlorine for the moment, a chlorine atom has a mass of 35.45 grams. Chlorine gas, which is a poisonous gas, and here's a picture of a flask, a sealed flask containing sort of greenish yellow chlorine gas. It's so reactive that it actually essentially doesn't exist in nature. All the chlorine gas that has been formed made by people. The atomic chlorine occurs in other forms in nature, but not as chlorine gas. Anyway, chlorine gas is not made up of single chlorine atoms. It's actually made up of molecules, each of which contains 2 chlorine atoms. And so if you wanted to know what the mass of a chlorine molecule is, you would simply say, okay, each chlorine molecule has 2 chlorine atoms. Each chlorine atom weighs 35.453 AMU. Therefore, a chlorine molecule has a mass of 70.906 AMU, rounded to 3 decimal places. Now that feeds into the concept of the mole, and you will, hopefully this will all kind of fit together in just a moment when I attempt to explain why. Teaching on the mole concept is always one of the most challenging things for a chemistry teacher, because once you get it, it's sort of like riding a bicycle. Once you get it, it's just kind of obvious to you, but then trying to explain to someone else how to ride a bicycle is always a bit of a tough task. Here's my best shot at trying to explain in a very short lesson the concept of the mole. Okay, so the mole is a counting unit, and you may remember in the video on units, the SI unit of amount of substance is the mole. It's similar to something like a dozen or a score or a gross. By the way, a gross, do you know how much that is? It's 144. But it's similar to something like a dozen, except instead of being 12, it is 602 with 21 zeros after it. So 602 billion trillion. That number, and when we write that in scientific notation, it's 6.02 times 10 to the 23rd. And I actually had indicated that in our video on scientific notation. It is named in honor of Amadeo, I think everybody knows the answer to this, Avogadro, who proposed that this number existed probably 100 years before the actual value of the number was worked out. He studied gases, and he figured out in his research that no matter what gas you used, whether it was oxygen or nitrogen or any other gas, equal volumes of different gases always contained equal numbers of particles or molecules. And so there is a picture of Mr. Avogadro. Okay, so why do we have this quantity, the mole? Well, chemists do chemical reactions, at least good chemists like I was when I was an industrial chemist. My job was to do, as a researcher, to do chemical reactions. In order to do that, you have to count out various amounts of this substance and that substance so that you have the right amounts. It's sort of like a recipe. You want to make sure you've got the right amounts of things. You don't just arbitrarily throw a couple different things together to do a chemical reaction. You try to combine them in the correct amounts. And so we need to be able to count out molecules or atoms in order to have the right amount to react with some quantity of molecules or atoms of a different substance. The issue is that these things are so tiny and their masses are so small that we can't really count them out. First of all, they're too small to actually be seen. So we can't actually count a thing out by looking at it. I'm giving you the example of a water molecule here. It actually, if you lined up 4 million water molecules side by side, that would have a length of 1 millimeter. So you can appreciate that they're impossible to count by viewing them. And then even if you could count out some quantity of water molecules, say 4 million of them, the mass of that would be so tiny that it would be a pointless thing to try and do some sort of a reaction on, because you wouldn't have enough material to care about. So we need a different way of counting things. And so we, as chemists, we count things the same way that perhaps someone who is going to build a large building, or at least a large deck in their backyard, goes and counts things when they go to Lowe's or Home Depot to buy stuff. Instead of counting by individually 1, 2, 3, 4 counting things out, we count by weighing. And so again, if it is typical to go to a hardware store, and if you need a large quantity of screws or nails or even washers or something like that, to purchase them not by a number of objects, but by a mass of objects. And so that's the same way we handle compounds and substances in chemistry. We count them by weighing. So that's why we need the mole, because these particles are too tiny to be able to count out or weigh out individually. We need to weigh out a large number of them. So we have this large quantity called the mole. Why this specific number, 6.02 times 10 to the 23rd? That turns out not to be an arbitrarily selected number. And this goes back to something I said a few minutes ago, which has to do with the mass of an AMU. And you may or may not remember that I said the mass of one atomic mass unit is 1.66 times 10 to the minus 24th grams. Well, it turns out that Avogadro's number, 6.02 times 10 to the 23rd, is simply the reciprocal of the mass of an atomic mass unit. So if you take 1 over 1.66 times 10 to the minus 24th, you get 6.02 times 10 to the 23rd. Well, why is that significant? Well, if there are 1.66 times 10 to the minus 24th grams per AMU, then when we take the reciprocal of the number, we also take the reciprocal of the units. That means that there are Avogadro's number of AMU per gram. So let me say that again. If there are 1.66 times 10 to the minus 24th grams per AMU, then there are 6.02 times 10 to the 23rd AMU per gram. Well, if there are that many AMU per gram, and there are that many objects in a mole of something, then it follows that if an object had a mass of exactly 1 AMU, then 1 mole of those objects would have a mass of exactly 1 gram. And if an object had a mass of 2 AMU, then 1 mole of those objects would have a mass of 2 grams, and etc. And so what this number, Avogadro's number, allows us to do is go directly from masses in AMU from the periodic table and transfer that into masses in grams, which is something that we can handle in a laboratory, weigh out on a balance, and is much easier to deal with. So let's just think through this a little bit more. I showed you a water molecule just a second ago. It turns out that if you calculate the mass of a water molecule, which has 1 oxygen atom and 2 hydrogen atoms, and so if you take 2 times the atomic mass of hydrogen and then add it to 1 times the atomic mass of oxygen, and round it to 2 decimal places, you get 18.02 AMU for 1 little tiny water molecule. Well, it follows based on the logic that I was just expressing on the previous slide, that if I've got 6.02 times 10 to the 23rd of those, or 1 mole of them, then that is going to have a mass of 18.02 grams. So let's just go back and try this again. If an object has a mass of 1 AMU, 1 mole of those objects would have a mass of 1 gram. If an object has a mass of 2 AMU, 1 mole of those objects would have a mass of 2 grams. If an object had a mass of 18.02 AMU, then 1 mole of those objects would have a mass of 18.02 grams. And if an object, say a chlorine molecule, had a mass of 70.9 AMU, then 1 mole of those objects would collectively have a mass of 70.9 grams. Let's think about this. Well, let me just say this. The 2 most important things to remember about the mole. The first is this. The mass of 1 mole of any substance is equal to the formula weight of that substance expressed in grams. And so in other words, if a molecule of methane gas weighs 16 AMU, then a mole of methane gas weighs 16 grams. If a molecule of water weighs 18 AMU, then a mole of water weighs 18 grams. So that's the first thing. The mass of a mole of any substance is equal to its formula weight expressed in grams. The second most important thing is that 1 mole of any substance contains the same number of particles as 1 mole of any other substance. So the actual value of Avogadro's number is not so important as simply knowing that it exists. A mole of water contains the same number of molecules as a mole of chlorine gas, which contains the same number of molecules as a mole of methane gas, which contains the same number of molecules as a mole of glucose, etc. Okay, one more way to look at this. If I've got a dozen cookies, I've got 12 cookies. And if I've got a mole of cookies, I've got Avogadro's number of cookies. If I've got a dozen cars, I've got 12 cars. And if I've got a mole of cars, then I've got Avogadro's number of cars. And if I've got a dozen, say, aluminum atoms, I've got 12 of those. And if I've got a mole of aluminum atoms, I've got Avogadro's number of aluminum atoms. What remains the same? What remains the same in each of these cases is the number of items that I have. What is different in each case is what the mass is, right? A mole of cars is going to weigh much more than a mole of cookies, and a mole of cookies is going to weigh much more than a mole of aluminum atoms. And so when it comes to the mole and comparing moles of different objects, what's the same in each case is the number of objects. What's different in each case is the mass. And we'll talk about that more in the next video, actually. So a mole of particles contains Avogadro's number of particles, and therefore we can say that a mole of carbon atoms contains Avogadro's number of carbon atoms. A mole of water contains Avogadro's number of water molecules. A mole of sodium chloride contains Avogadro's number of sodium chloride molecules. This also allows us to consider Avogadro's number as a conversion factor, and this is now going to allow us to get into some dimensional analysis problems like we saw in a previous video. So since 1 mole equals 6.02 times 10 to the 23rd particles, then I can write that as a conversion factor, either as 6.02 times 10 to the 23rd particles per mole, or 1 mole per 6.02 times 10 to the 23rd particles. Again, being mindful that a particle, depending on what the substance is, could be either an atom or a molecule. Okay. Hooray, that allows us to do a little quick pop quiz here. So here's the question. How many atoms are there in 0.5 moles of aluminum? You have 3 possible answers here, and so you can pause the video if you'd like, try the problem, and then start the video back up. Okay, the answer is that if I've got 0.500 moles of aluminum, and using the conversion factors from the previous page, that 1 mole of aluminum contains 6.02 times 10 to the 23rd atoms. I set this up so that moles of aluminum cancel out. I am left with 3.01 times 10 to the 23rd atoms. The correct answer is C. One more. How many moles of sulfur are there in 1.8 times 10 to the 24th sulfur atoms? Pause the video, try the problem, then turn it back on. Okay, the measurement I am starting with is 1.8 times 10 to the 24th sulfur atoms. I'm now going to use the conversion, the reciprocal conversion factor, that there is 1 mole for every 6.02 times 10 to the 23rd atoms. Atoms cancel out. I divide 1.8 times 10 to the 4th, 1.8 times 10 to the 24th by 6.02 times 10 to the 23rd, and I get 3 moles of sulfur. The correct answer is B. Okay, there are several resources for this video in the worksheets folder: a periodic table, the list of the 45 common elements I want you to know, and then a quiz on correlating names with symbols, and as well as some worksheet problems on converting moles to numbers of particles and vice versa. So we will talk to you again soon.